In another segment, we've discussed that the dissipation of electromagnetic energy in a medium for a monochromatic wave is proportional to the imaginary part of the dielectric constant at that frequency. Now we'll discuss how and under what conditions one can define an effective energy for the electromagnetic field in a medium. We return to the energy balance equation, J dot E equals negative del S minus E d dot plus H b dot, and we'll work with the term E d dot. So we'll write it in terms of the Fourier transform, both the E and D. So by definition, E of t can be written as the integral over frequencies, the Fourier transform of omega, e to the minus I omega t, d omega, and an almost identical expression for d of omega, just e replaced by d. Now we can write the expression for d dot as a function of time. So in a similar expression as we have here, we differentiate the right-hand side with respect to time. So this brings down the factor minus I omega t from the exponent. And here I have d of omega, and same thing here. And we also recall that from the convolution rule, d of omega is equal to epsilon of omega times E of omega. And now I'm going to write the expression for E d dot as a function of time by simply writing down the product of E of t and d of t. And I'm going to use omega prime in the integral for E of t. And I'll take a complex conjugate for convenience. So E of t is real, so I can take a complex conjugate on the right-hand side. So overall, I have a double integral over frequencies. So d omega prime and d omega. I have a complex conjugate on the left-hand side, so I have E star of omega prime, e to the I omega prime t, minus I omega, epsilon of omega, E of omega, e to the minus I omega t. And now I can take the two exponential terms and combine them in one. So here I'll have omega minus omega prime t. Now, it is not possible to define effective energy in the absolutely general case of fields with an arbitrary time dependence. But one can do it in the following special case. So we have previously considered a monochromatic wave and looked at the dissipation. That would be the time average of E d dot for the fields with a constant frequency. Now, if the wave is monochromatic, it's just some amplitude times a harmonic function. So on average, the fields don't change, so the energy obviously stays constant, and there's no way to make any progress. Nothing is changing. Now, instead, we can consider a wave where the spectrum is localized around a certain frequency but has a small but finite extent. So that means that if we look at the waveform, we will see something like this. So here's our function of time. It looks like a monochromatic wave with an envelope superimposed on top of it. So it's oscillating at a given carrier frequency, but the amplitude slowly changes in time. Now this is just an example. I just took a Gaussian function and multiplied by some harmonic sine wave. But the essential thing is that it's a oscillating function times a slowly varying envelope. So a function like this can be written as f of t equals some envelope function f, call it f sub env of t, times an exponent with some fixed carrier frequency omega. Now, of course, as usual, we'll put the real part here. The Fourier transform of such a waveform will have peaks at plus and minus omega naught, something like this. Here, the real part of f of omega is shown in blue, and the imaginary part is shown in yellow. Notice, by the way, that because f of t is a real function, then it follows that f of omega equals f star of minus omega. So the real part of f of omega is an even function, and the imaginary part is an odd function. So in the picture here, what is shown is exactly the Fourier transform of the function shown up here. So we have peaks around 2 and minus 2. So 2 and minus 2 are the frequencies omega naught in this function. So this is generally how a Fourier transform of any function will look like that is formed out of a product of a carrier harmonic function and a slowly varying envelope function. The peaks at plus and minus omega naught, in this particular case, they look like Gaussian functions because I took a Gaussian exponent, Gaussian envelope, and generally just some functions around omega naught will represent the Fourier transform form of the envelope function. So the goal would be to reduce the product ed dot, where E and D are given by waveforms like that, and we'll want to reduce this product to a time derivative of some effective energy function in a coarse-grained way, in the sense that we'll not be interested in the variation of energy over one individual period of oscillation, but we'll be interested in the slow variation of average energy over multiple periods, just due to the changing envelope. So once we can reduce this to a time derivative of some function, we will be able to associate that function to the average effective energy of the field. So with this assumption for the electric field, we know that E of t can now be written as sum of two complex conjugate quantities. So we'll write this as E envelope of t, e to the minus I omega naught t, plus the complex conjugate term, and if we look at the integral for ed dot over frequencies, so we see that in order for the integrand to be appreciable, both frequencies have to be close to omega naught or minus I omega naught. Otherwise, the amplitudes, at least one of them, will be negligible. The support for the Fourier transform of omega is localized around plus and minus omega naught. So the integral splits in four regions in omega prime plane, right? So we can represent this integral in omega prime plane. It's the domain of this integral, and the important contributions come from four regions in space around omega naught and plus or minus omega naught for both variables. As I mentioned, we're only interested in the slowly varying part of ed dot. We're not interested in a quickly varying piece that varies in the course of one oscillation. So we want to have in mind the average of this quantity over a few periods of oscillation. Now let's look at the right-hand side. Here we have this exponent where we have a difference in frequencies. So if omega and omega prime are approximately equal, that means we're looking at this region of integration or this region of integration, then the omega naught will cancel out of omega minus omega t. And here we have an exponent with a small difference in frequencies. That's of the order of the size of this region, or of the order of the width of the Fourier transform peaks. So that's the same thing as the width of the Fourier transform of the slowly varying envelope function. So we keep these terms because they vary slowly in time. But if omega and omega prime have opposite signs, which means we're dealing with this region or this region, in the exponent we'll have either twice omega naught or minus twice omega naught. That will be a quickly varying part of ed dot, and if we average over a few periods of oscillation, these terms will cancel out to zero. So what remains are two regions for omega and omega prime close to either plus omega naught or minus omega naught. So let's take those two pieces and manipulate on one of them for negative frequencies so that we can write the whole expression in a more convenient way. So let's write down what we need to do. So two regions. Region 1, omega, approximately equal omega prime, approximately equal omega naught. Second region, approximately equal to minus omega naught. So now we're looking at region 2. So for region 2, we have the integral over negative frequencies, d omega prime, and here's everything that sits here. In this integral, we'll do the following. We will swap omega and omega prime, just relabel them, and at the same time change the sign of the integration variables. So we're swapping them and changing signs. This will now give us the integral over positive frequencies, everywhere where we had omega prime, we'll have omega. So the first term becomes E star of minus omega. Remember, we're changing sign and interchanging primed and unprimed. I omega prime, epsilon of minus omega prime, E of minus omega prime, and here I have the same exponent as before. Now I can use the fact that the E field is real, and therefore, as usual for the real field, the Fourier transform satisfies this equation. That the E of omega is equal to E star of minus omega. So in the first term, here, I can remove the star and the minus sign for the frequency. In the second appearance of the electric field, I can do the same. Now I have to add a star and remove the minus sign. And I can do the same thing for epsilon. Remember, epsilon is also a real function. So I can eliminate the minus sign here and add the complex conjugate at the same time. So now I can take this term and add it to the part of the integral for region number 1. So if we look at the integrand, E of omega is there, E star of omega prime is there. The time-dependent exponent is there, but there are some modifications in the other factors. So if I put this together, I can now write for ED dot, which is averaged over a few oscillation periods. So it's the slowly varying part of ED dot, is given by the integral now over positive frequencies only. I have E of omega, E star of omega prime. And now I have I omega prime epsilon star of omega prime minus omega epsilon of omega, and the exponent. At this point, we'll assume that the medium is transparent in the given frequency range. So we'll assume that the imaginary part of epsilon of omega naught and near it is close to zero. So we assume this. With this assumption, there is no difference between epsilon star and epsilon in this expression. And then this bracket looks like the difference in the values of the same function, omega times epsilon of omega, taken at two frequencies, omega and omega prime, which are close to omega naught, both of them. So the difference between omega prime and omega that is important in this integral is small, and therefore we can expand this bracket to first order in the difference of omega and omega prime. So expanding to first order, we can write this as approximately omega prime minus omega times d by d omega, omega epsilon of omega, and all of this evaluated at omega equal omega naught. So this derivative here becomes just a number. This is just a number in the Taylor expansion of this quantity around omega naught. So this can be taken outside of the integral. What remains under the integral is just omega prime minus omega. To further simplify, remember our goal is to write this whole thing in terms of the time derivative of some function. We can notice that in order to generate the factor omega prime minus omega under the integral, we can differentiate the whole thing with respect to time. Time appears only in the exponent. If we do d by dt, it will pull down minus I times omega minus omega prime. So we can rewrite this whole integral as the constant term that I'll write like this, and then d by dt, the integral of d omega prime d omega e of omega e star of omega prime, the complex exponent, and that's it. Now let's look at this integral. It looks exactly like the square of e of t, except that the integral goes from 0 to infinity. The integral of e of t contains d omega, e of omega, e to the minus I omega t. But here we have a product of two terms, complex conjugates of each other, but e of t is real. So if the integral went from minus infinity to infinity, this would just be e of t squared. Now we can use the same considerations that we used before to eliminate the two parts of the integral with omega and omega prime lying in the second and fourth quadrant, because they represented the quickly varying part of ED dot. Now here we kept only the terms in the first and third quadrant to represent the slow variation of ED dot. We can use the same idea to relate this to the slow part of E of t squared. If we started with just E dot E and followed exactly the same procedure as we used before for ED dot, we will find that it's equal to 2 d by dt, and then here goes the same integral as in this line above. So the factor of 2 comes from transforming the integral over negative frequencies to the 1 over positive ones. And in this case they're equal, so you get a factor of 2. Taking this into account, we can write that ED dot slow is given by the time derivative of a quantity that we can call U effective, and U effective is given by 1/2 the average of E squared slow times by d by d omega naught epsilon of omega naught. This can be viewed as effective energy because it's related to the work done by the electromagnetic field. Right? The left-hand side came from the expression for J dot E that expresses the work done by the field on the charges that are considered external to the system. That's the current density that appears in Maxwell's equations that also contains the polarization, and the polarization is included in epsilon. So the total charge and current densities are split in two parts, the formally external ones and formally internal, and the work on the external currents is expressed in terms of this effective energy density that includes the dielectric response function. This treatment was first proposed by Brillouin, and therefore it's usually called the Brillouin energy density. Notice that in the case of a medium with instantaneous response, where epsilon of omega is just a constant, the derivative in the formula becomes just epsilon, and U effective turns into 1/2 E squared times epsilon. This is the same expression that we had in vacuum, or we would have if we just started with ED dot and D simply equal to epsilon E for instantaneous response. There is, of course, a piece corresponding to the magnetic field, corresponding to HB dot, that we didn't write down. Of course, it should also appear in the Brillouin formula. This concludes this segment where we discussed how effective energy density may be introduced for a nearly monochromatic wave propagating through a transparent medium.